Good morning, all. Welcome back to the class. I hope you are keeping well, you are healthy, take care of your health. Weather is changing, so you have to be careful. Well, going beyond, we have already last time discussed about the graphs, and I'm sure some of you have implemented, but graphs, what we started, we have seen the graph storage and graphs being used. Let me just change the pen style. This works slightly better. So for the graphs, we have seen the adjacency matrix and adjacency list and basic operations. And that's what we have discussed last time. I'm sure some of you have definitely implemented, and using both of these, I gave last time certain operations to be tried. I'm sure many of you have done. And then if you have practiced well, today's lecture will be very easy. Those who have not practiced, those who have not coded, for them, for their benefit, I'm just going to have a look on the implementation aspect of these things, so that before we proceed for better algorithms of this, it will be more easy for you to grasp and help. If you have already done, you can compare your implementation. For better understanding, it will be useful now to have a look, and then you must do of your own, but I'm showing you some sample code so that you can feel better in today's lecture. So let me just have this stored and then go to the lecture. So I'm sure you can see my screen. So this is, I'm showing you the adjacency list implementation, assuming that adjacency matrix you are comfortable, and probably 2D array programming you can easily do. So effectively, max I have defined here as 20, so maximum 20 nodes, node structure having vertex and node pointer, and then there are certain functions. Effectively, what I need is a graph to be declared. So I'll just go into the main and show you what will be the graph declaration. So here, graph max. Max will mean maximum I can have 20 nodes. In this programming, I'm using 1 to n. So effectively, that means 19 can be the maximum value of n. I equal to 0, I am not using during the coding, although it is good, but normally vertices are not numbered from 0. So I have avoided being using 0 as a vertex ID. So 1 to n used. So if I give n 19, only then I will be able to use 1 to 19 indexes. And if I give max n as a 20, that I will be using graph stair 20, which is not permitted because maximum 20 index 20 values are being stored in this. So 0 to 90, and 0 I am wasting. So maximum 19 I can use. But so accordingly, you can plan. So I'm giving here a choice: read a graph, count adjacent of a vertex, find vertex having highest outgoing connections, having no connection, find the vertex having maximum vertices outgoing, display adjacency list, find the vertex. Maybe I can have another one having maximum incoming edges. So maybe I can have that also choice. For example, I think I have that also, maximum incoming as 5. So find vertex who's to whom it is connected. So to whom effectively means that incoming. So effectively, I'm saying incoming edges are being considered here, as I discussed last time. So based on that, let's go one by one. Let's have a quick look on how do I read. Last time I told you that reading can be either adjacency matrix based or can be adjacent by reading the adjacent vertices of a particular node. So this is the second method implemented. From 1 to n I'm using. Out of this, I ask the user enter adjacent vertices of any node, say percentage ID. So I will change or as -1 to stop. Until I don't give -1, I read the vertex ID. And then I'm calling graph I equal to insert. So this I will remove, and graph I equal to insert. So corresponding to that graph, I'm going to have the edge being inserted. So how edge will be inserted? Simple. If graph I is initially null, then I'm going to add this as a initial node. Graph I effectively means it's a starting pointer. So you can say here, I'm calling the insert. It is very similar to what insertion in a singly linked list you have implemented in data structures. So more or less, this is the same thing. I have done a malloc initially making temp arrow next equal to null, vertex being passed the corresponding value. And then I say if a start equal to null, means if a graph I is null, then graph I will change. And why it will change? I'm passing here node star graph I. So I'm passing here graph I, which will be allowed to have the corresponding address or the corresponding new pointer changing. Graph is an array by default passed. So in array, call by reference automatically happen. So no call by value issue will come. Graph is an array being passed, and in array any changes are automatically done. So I'm saying graph I equal to insert. Otherwise also I'm saying graph I being assigned the new changed value. So here this will be assigned. Start will be becoming next node. Later, of course, I have the return start. Otherwise, here now I am doing inserting the new edge at the start of this linked list. Well, as I have written, normally in linked list creation, we insert at the end, but here I am doing at the start. Reason is in the graph, we already said that edges are by default unordered. So we can insert anywhere, and inserting at the start helps me unit time insertion. So I'm able to do unit time insertion, that is order of 1, even if I have some nodes there. If I take it to the last, obviously it will take more space or more time, not space, more time it will take, and that way I will be having on. But this is the purpose of this. So this becomes insertion, and accordingly my adjacency list for every node will be prepared by reading from the graph and then going all that. So this becomes insertion. Then coming to various operations, or before that, let me understand what can be other ways of reading. So going to the main, here I have said read a graph. So for the reading also, I have given multiple choices, and a read graph, I'll show you how do I read. So read graph, I'm saying there are one way, read adjacency list using matrix, read adjacent vertex one by one, and this is another third method, which I'll demonstrate. Second method was what we have just seen, that I enter number of adjacent vertices till I don't press -1 for each vertex. So other method where I enter the adjacency matrix, as last time we discussed, directly n into n matrix is read. Only change here I have done is matrix is not being stored. I directly read whether ij value is 1 or 0. So correspondingly, if value is 1, I am assuming that is a vertex to be added. So graph I becomes a vertex being added, and in the graph ij vertex will be added. So, and that will be inserted using the insert command, which we have already implemented. So here using adjacency matrix also I can read, and then I'm not storing adjacency matrix. Third method, I can read vertices by all vertices by showing the user a message that is there an edge between ij. So I'll give him all permutations that 1, 2 is there an edge, 1, 3 is there an edge, 1, 4 is there an edge, 1, 5 edge, etc., etc. Then 2, 1, 2, 3, I not equal to j, so that self-looping is not considered. And accordingly, if the user says, yes, there is an edge between 2, 3. So in the graph 2, I will insert the edge 2, 3. If user says there is an edge between 2, 5, accordingly that. And so this can be third way of reading. Here, I don't ask the user to enter the adjacent vertex IDs. I give him a choice. Tell me, is there an edge between 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 3, 2, 4, 2, 5, 3, 1, 3, 3, 3, 2, 3, 4, 3, 5, and so on. Having said that, let's have a basic look on various operations. So, for example, after insertion, I have count of the vertices or count of outgoing edges for a particular vertex. Which vertex? Say I pass here. Based on the pass, I will say, fine, I'm going to start with this particular one, that I will say temp I am taking. Temp is equivalent to start of the corresponding adjacency list. So if my vertex is 3, I say temp equal to graph 3, means temp is equivalent to start of third adjacency list. That means corresponding to vertex 3, adjacency list is effectively nothing but a singly linked list. Effectively, I am traversing that singly linked list and counting, and then count is returned. But this module will be useful to me at many stages. For example, now I want to find which node has highest outgoing edges. So no specific number. Intentionally, I have given a different variable name. It's not compulsory that you every time write graph. You can give a different name as a formal parameter. You should know what is a formal parameter and what are actual values. So, but this is what is a formal parameter. If I use word G, I can call here, or I can use this word G subsequently. So I am having highest connect. So I will calculate the count for every vertex. And if the count is greater than previous maximum, maximum will be updated, corresponding vertex index will be stored, and finally the vertex will be returned. So using count adjacent outgoing edges for every vertex will be counted, and then I will be able to return back the vertex having highest count. No connection. I want to find out a vertex which has no connections, means no outgoing, no incoming. So the logic which I am using, I'm making an array of n plus 1 because 1 to n I am using. So array n plus 1 is needed. 0 is not being used. So 1 to n indexes will be used. Hence, declaration has to be n plus 1. So initially, I say array I is going to count number of incoming edges to every node. So for that, I initialize it with 0. And here I count the corresponding incoming edge. Because in case of adjacency matrix, I don't have a column-wise processing possible. So row-wise or outgoing edges-wise adjacency list is to be traversed. And if I find some vertex has some outgoing edge coming to this, that becomes incoming edge to this. So if, for example, I started from graph 1, and I'll say I have to start from graph 1, not next. This was incorrect. So I'm correcting this. And from graph 1, I started, and then I'll say first vertex I will take, and say from graph 1, I have vertices 2 and 4 connected. So 1, 2 is an edge. So for vertex 2, there is an incoming edge. 1, 4 is an edge. For vertex 4, this is an incoming edge. For every such vertex, I will calculate. Then I will go to the second adjacency list. All adjacent nodes of second will also get incremented for the corresponding incoming edges. So now in array I have got all incoming edge count. Then I'll check for each array I to be checked whether if that is 0, means incoming edges to that are 0. If the incoming are 0, then I will count its adjacent or its outgoing edges. So corresponding to vertex J, who has incoming 0, I count its outgoing. If the count again comes out to be 0, incoming was already 0, outgoing is 0. So I can say this is the vertex which has got no incoming or outgoing, or it is unconnected. Of course, through this process, I will get returned only single edge, which is unconnected. If I want all such edges to be returned, I need to store all such edges somewhere into an array or a structure and return that array or structure. In this case, first unconnected edge will get returned and I am not process further. If nothing happens, I'll return them. Similarly, if I want to find, like last time I gave you, find the vertex with minimum incoming. Here the code is written for maximum incoming, similar one. And here initially, more or less the logic remains just we discussed. I initialize incoming count as a 0. Then correspondingly, the count based, each of that will be counted. And corresponding to that, while traversing outgoing edges, the corresponding incoming counter will be incremented. And once I have incremented, I will find maximum. And once I have got the maximum found, the return edge or max index will be returned. So this way, I'll be finding the vertex with maximum incoming edges. So this is the way we are going to have all this stored. And this is the program which you should have implemented. If you have done good enough, if you have not done, maybe now you can do, but we resume with the next discussions, which are more important discussions on graphs. But for better understanding of graphs, coming algorithm, this clarity of adjacency list-based implementation is must, because most of our programming is going to be now adjacency list-based. So you must know how it will be working. So I will be talking of all algorithms, almost all of them, on basis of adjacency list. Of course, adjacency matrix is also possible, but that is easy because it's a 2D array program. So I'm sure if you know adjacency list programming, you can also do the adjacency matrix programming also. So you should practice both, but adjacency list will be more used. Now, the first operation which we talk today is traversal algorithms. So traversal algos, primarily they are traversal algo, although they are named in a different manner. There are two traversal algos. One is called as a depth first search, and other is called as breadth first search. The word search is used because these algorithms are very frequently used in many varieties for searching of various graphs or similar structures. But here they are effectively traversal algos. So for the time being, they are traversal algos. Like in a tree, you had in order, pre-order, or post-order traversals. So they were traversal to go through every node. Here also they are traversals, but the methodology of traversal will be different. In one case, it is depth-based. Other case, it is going to be breadth-based. Today, we are going to talk of a DFS, and next class, we will talk of breadth first. Today, I'm going a bit slow. I'm giving you time so that you can grasp and start working on graphs. Otherwise, DFS and BFS can be covered in one lecture also, but I'll cover DFS today. We are going to today understand and design DFS. Next class, we are going to do BFS design plus, and plus we are going to do along with BFS analysis or time complexity of analysis of DFS and BS. So that we will do in the coming class. But today we are going to talk of DFS mainly, and it will give you time to practice and understand these concepts also. So let's understand how DFS works. Depth first. Why do we say depth? After a few minutes, I'll explain and it will be more clear. But before that, let me draw a graph which I'm going to use. Say I have 1. Let's say I have here 3. I have here, say, 5. I have this side, let's say I have a 2. Then from 2, I have, let's say, 4 connected. From 4, this side connected. From 3, this side connected. Let's say these are outgoing edges or incoming available. And maybe, let's say I have a 6. Then I have a 7. And maybe I have connections like this. Or maybe connections, I have something like this. So anything like this connected, and 6 I am keeping intentionally unconnected so that we know how to handle this. By default, I am taking the directed graph, but if you know the directed graphs working, undirected will be even easier because all that things will be similar plus easier. And if you know directed, easily you can write for the undirected. So depth first, primarily we start from any vertex, normally from the starting vertex. So that is from the vertex 1, but there is no compulsion that you have to start here. But because in this case, there is no root. In a tree, you have a root and you start from the root. Here, there is no root. But normally, we start from the starting vertex. That will mean effectively 1 in this case, vertex 1. So I start with 1. What it will mean? From here, I will start. 1 will be displayed as a traversal process done. And then from 1, I will go one by one to its outgoing edges. Outgoing edges means its adjacents. So one has 3 adjacents. Say one's adjacents are, I have 3, 5, and 2. Let's assume they are stored in this order. If they are stored in this order, first of all, I will start with the 3. Now, 3 means I will print 3, but now I will resume from 3 onwards. Again, a DFS to be applied on 3. So that will mean other adjacents of 1 will be still uncovered and waiting, but 3 onwards I will start. From 3, again I will say 3 is a traversed. So I will know which is untraversed, which is a traversed, so that I don't get into a cycle. For example, if I have a cycle like this, I might be having continuously roaming around the cycle. So loop or cycle can exist, and my algo should not go into a cycle. So I have to take care of this issue also. So I will maintain which node is untraversed and which node is traversed. And initially, all nodes are traversed. And whenever I am able to traverse that, I will change its status to call it as a traversed. So status, that means the status needs to be stored. And of course, we will need extra storage for this. So assume that, yes, we will store somewhere. So I'll say, fine, 3 was untraversed. I have now printed 3 and resume from 3. 3 means 3 is adjacents to be seen. 3 has only one adjacent, which is a 5. 5 is untraversed. So 5 is untraversed means I will go to 5, print the 5 here, and I will list here 5. And now 5 is also traversed, and I will go to traverse list of 5 or adjacency list of 5. 5 has no adjacency list. 5 has no adjacency list means I have nothing more from 5 onwards. As soon as nothing onwards available, I will backtrack. Backtrack to the previous one. Backtrack to the previous means to 5 I came via 3. So I will go back to 3 to check its untraversed adjacents. I go back to 3. From 3, there is no extra outgoing edge beyond 5. That means 3 is also over. Further backtrack. Further backtrack means go to 1. 1's untraversed outgoing edges again to be traversed. 1's outgoing edges were 5 and 2. So I resume at 5. I am resuming at 5. I know that now I am this 5. 5 is already traversed. I have already done. So 5 is also not to be done further. If it is untraversed only, I'll go. Otherwise, 5 is already traversed. So then I say, go to the next untraversed adjacent of 1, 2. 2 is untraversed. I have seen 2 is not listed. So 2 is untraversed. I will go to 2. Going to 2 means I treat 2 as a traversed. 2 is listed. And now 2 onwards, DFS will start working. 2 onwards means 2's outgoing edge is to be seen. 2 has this, let's say, edge 8, and 2 has edge 7. So if their 2's adjacents are, let's say, listed in the order of 8 and 7, first I will go to 8, reach to 8, and I see 8 is untraversed. So 8 will be listed here. After 8 now, DFS on 8 will be applied. 8 says I have an outgoing edge to 5 only. 5 is already traversed, so nothing to be done. Resume back to 2. 2 is having adjacent 7 still untraversed, so 7 will be traversed. 7 comes here, and then DFS applied on 7. I go to 7 node. 7 has outgoing edge towards 3. 3 is already traversed. I am supposed to go towards untraversed only. So DFS over. Over means go back and resume. From here, 8 was having already nothing. So from 2 steps to 7, I reached not via 8. I reached to 7 via 2. So I will resume to 2. 2 had 8 and 7 over, nothing else remaining. From 2, resume back, backtrack. 2, I reached from 1. I know that from this 2, I reached via 1. So I resume back from 2 to this 1. And from 1, now I see any more adjacents which are untraversed. 1's adjacent were 3 or 3, 5, and 2 already covered. 2 also covered. Nothing left. Nothing left will mean, again, I have to find out any vertex which is untraversed and resume the process. So I find 1 is already traversed, 2 is already traversed, 3 is already traversed. There was, let's assume, some 4 node also. So maybe this was 4 or 8, whatever you say. So that is already traversed. 5 is already traversed. 6 I find untraversed. So I will start with the 6, traverse 6, and apply DFS on 6 adjacents. 6 has no outgoing, so 6 also does nothing. Resume back, resuming nothing because 6 was not started from any node. Again, I have to look for any untraversed node. 7 is already traversed. If existed 8 also traversed, everything over. DFS over. So accordingly, I have got all this done, and this is the way my algorithm is going to work. Now, having clearly understood, I repeat what we did. So the logic or the process effectively is that in this case, this effectively explores the outgoing edges out of one untraversed vertex. I'm going to explore outgoing edges out of untraversed vertices one by one. So this is the first step, untraversed vertices one by one, of course. But one by one means that one by one will come later. Later, I will say edges out of most recent, or I'll say most recent untraversed. That word will help me to understand what does it mean. Most recently untraversed vertex, I'll say. Instead of vertices, I will say vertex, so that at a time I am considering one. And whichever, so I will say untraversed will be treated as a traversed. Treat it as a traversed now. So that will be first thing. Once I have treated it a traverse, then I will say explore its untraversed adjacents using the DFS logic itself. So using DFS, it effectively means a recursion is going to come into picture automatically, because while talking logic of DFS, I'm repeating this step repeatedly. So again, I will treat it, go to another untraversed, treat that as a traverse, explore its untraversed vertices. If no untraversed available as its adjacent, then I'm going to backtrack. And recursion automatically backtracks. So backtrack to the previous node, and from there onwards, you are going to go towards backtrack and resume from the previous. Just previous or previous reset. So that is the overall logic. For example, I said one was initially untraversed. So I started from one. From one, I had its 3, 5, and 2, but I went to 3. 3 is like previous slide. I can say from 1 to 3. From 3, its adjacents were 5. So I went to 5. I went to 5's adjacents, not available. Then like I say that from 5, I had no adjacents. So I resumed from 5 back to 3. 3 had some adjacents. Yes, 3 had no more adjacents. So I resumed back to 1. From 1, I went to, then after 3, 5, then I went to 2. From 2, again, I went to recursively towards the 2's adjacents. From 2 adjacents, you can see from 2, I went to 8 and 7 are adjacents of 2. So from 2, recursively, I went to 8. From 8 onwards, there was no adjacent. So I backtracked. From backtracking, then I went from 2 to 7. From 7, again, DFS to be applied. No DFS available, again backtracked. From 2 also nothing available. No, from then again backtracked. From 1, nothing untraversed available now. So then I restarted with this step. Most recently untraversed, 1 available. So one by one I traversed. Effectively, I started 1 onwards and everything covered. After 1, then I will say, now I am going to resume with the 6. So 1 by 1 from 1, rest all in between 1, 2, 5, 1, 2, 3, 4, 5 were already covered. I resumed at 6. After that also all covered. So this is the logic. So based on this, let's start the design aspect. as you are new to the graph programming, so partially I'm going to show you the coding and rest you can complete. But later, of course, you will do most of the coding. I will just tell the logic. So partial coding we are going to see today. So, of course, I will have now a requirement of a traversed to be stored. So I will say traversed status I need to store for each vertex. So I will require extra data structure. For each vertex, I need this. So I need to have storage. Before going that, let's understand why did I say depth first? Because from 1, I had possibility to traverse 3, 5, and 2 all, but I didn't go to all of these 1. From 1, I went to 3. From 3, it went to 5. And once I was able to do all that, then only I went to 2. From 2, I went to 8. From 8, I went to 7. And like that, and then resumed, and then I went to another 6. So every time I go depth-wise, and one depth-based tree is traversed. Every time depth-based tree of some nodes of some connected vertices gets covered. Some connected vertices, of course, get covered or get visited. So I will say I will have one extra array taken, which I will name as visited, to note that if visited is a 0 or 1. So visited array I will take, and it will be array for n plus 1, because 0 to n plus 1 needed, as 1 to n are my extra. So what is my implementation? First thing, I have my graph structure available. Graph is an array. I am storing this 0. I am not using. By default, it has a 0 also. It will be unused. But from 1 to n, I am going to store the corresponding adjacency lists. All that being there. For example, for 1, I have here 3, 5, and 2, and similarly for the others. Now I take extra, so this is there. I take for the time being one extra global array, which I call as visited. And that will be also an array of 0 to n or something, 0 unused. And 1 onwards, I will say, initially I will put 0, 0, 0. And later I will change status, where 0 means unvisited or untraversed, and 1 will mean traversed or visited. So I will use extra array global, because every time I change, it can be used. Of course, can be taken as a parameter also, but too many parameters, you might get confused. So I am not for the time being assuming it as a parameter, but it can be definitely taken as a parameter also. But 1 will mean traversed or visited. Then for our logic, only this was needed. For future programming or for future algos, we will also need a parent array, which will store the node through which I reached to this node for traverse. So parent 1 onwards will also store up to n. For example, I say 2, 1, I reached via no parent. It was a starting. So I will say its a parent was found to be -1. Initially, I will keep everyone -1. But later, once I say that from 1, first time I went to 3. So 3 node I reached via 1 node. So 3 is a parent. Parent of 3 will be called as 1. Because I reached to node 3 by traversing adjacents of 1. Similarly, from 3, later, let's say this is 5. and I have many more like that. So 5's parent will be 3, as if you see earlier, 2 node 5, so 2 node 5, I reached via this particular. Due to depth first applied on 3, I reached to this node. So 5's parent will be 3. Parent is this. 3's parent was 1. Like 8's parents will be 2. 7's parent will be 2. 8's and 7's both parent will be 2, because 8 also come via 2 and this. So this parent I will need later, and I will store this. So later algos will need that, and that's why I'm initially storing, but for the time being it will not be used, and will need that. So we assume that this is also taken as a global array, and accordingly I will do. So now go to the programming. Of course, I have node star graph, let's say 20 or 21, whatever you say. Then I have int visited, and maybe whatever max or max plus 1 you require. Similarly, here you can have, let's say, max plus 1 if you require, whatever you say, if you have declared max as some variable. And you also need int parent as max plus 1. So I have 3 data structures. For the time being, I assume these to be global. And of course, this also can be global, but because this I will be using in every graph everywhere, so I'm just showing you how to pass it as a parameter, and these global for the time. So graph is always to be passed and other. So let's start programming. Probably it can be void. If I need something else, I will change it. Whatever syntax you require to put, but ultimately graph also needs to be sent, and n also needs to be sent. If I require something more, can be there, or if not global, visited and parent also can be there. First thing, I said all unvisited vertices are to be traversed one by one. All unvisited, but one by one. And once you go to somebody, you have to that is most recent visited, you have to explore that. But if there is unvisited, then only I will be going and do something. So that means somewhere I'm going to write, if a visited I equal to 0, then I'm going to make some call here for the recursive, etc. Explore or recursively do that. Explore its adjacents, and of course, before explore, I will say treat it as traversed, and then or treat it as visited and explore. Treat it as visited and explore its unvisited or its untraversed adjacents, So that logic is going to be there, but how to do, we will see, and how I will count. Of course, I said we will start with 1, but anytime once this exploration becomes over and no backtracking possible, then I have to find out another vertex which is untraversed. That straight away means I will need a loop for I is equal to 1 to n, and I will change, and first time I will be 1, guaranteedly it is unvisited. Later some in between will get visited. For example, in our case, when I was 1, that was once this use, and later when I was 6, then also this got used in our case. But from case to case, it will vary. So I will say, effectively, this is going to be my logic. Now I have to think of what I am going to write here. So how to do this? As I know, this is going to be recursively to be used. So this routine I'm going to write in a different manner. What I will write? Now, effectively, I say, let's make a recursive routine to be called in this situation, and I will have this call to be made for the recursive one. And that function I assume to be named as, let's say, DFS visit, and everything we will do. Of course, a graph and an are to be passed, but do I need something more to be passed? Yes, because I said treat ith vertex as visited and explore ith visit at vertex vertices or adjacents. That means this function also needs I to be passed, the vertex which is to be explored, vertex to be visited and explored. So now I need vertex to be visited and to be explored. So this I will be passed. In this case, as you can see, I didn't require till now any parent or till any visited status. So I assume everything of that will be done in a DFS function. So effectively, this will make sure that all vertices get covered, and even if unconnected, all will get covered, even if unconnected. So that is the purpose of this routine, but this is non-recursive. So even if it is unconnected, we are able to reach to every vertex. Then comes a DFS visit. So probably it can be void, but if you require later, we might find that, yes, if I have to change, I will do. Of course, all syntax to be passed, but I is guaranteedly needed. So you have all that graph, etc., and other global arrays available. Now I say, what was my step? First step was, I said, treat it as visited. So I will say visited of I to be called as 1. So that later I don't treat it further for as untraversed or unvisited. I said visiting also means a printf. So I will printf, and this I will be displayed also, so that a traversal gets the corresponding listing in a depth first order. Then, now what I have to do? Explore its edges, explore its unvisited edges or untraversed edges. But that also only if they are explored, then I have to do DFS recursion also, and DFS recursion also. That means I have to ultimately go through a full list of this. So maybe I can say I will get its adjacency list. So temp, I take, let's say, graph I, where temp becomes nothing but it's the start pointer of adjacency list of graph I. And of course, I said its adjacency edges one by one all to be traversed, because backtracking also will be needed, and backtracking should resume from the previous vertex and uncovered edges again to be done. That means all vertices or all adjacents are to be explored. So I can say effectively I will need while and complete traversal, something like while temp not equal to null or something like this. And now I will find first adjacent untraversed, first untraversed or unvisited adjacent, or find an untraversed adjacent one by one. Means what? Effectively, I will say, let's say j equal to, which is the next adjacent, find out in the j, or I will say the adjacent vertex, adj vertex, adj v equal to next adjacent of this I, and I will check if it is a traversed or not. If visited of adjacent vertex, this current adjacent vertex, if this is equal to 0, what I have to do? I have to recursively go to this itself. So this routine itself will be DFS visited. I'll just say that before that, I'll have something done. So I will say, here I am going to do DFS visit of this vertex or I'll say this is a recursive call. So whatever parameters for adjacent vertex, repeat this process, repeat this recursive. And automatically, whenever over will resume and at the next vertex, resume at next adjacent vertex, next adjacent V. So automatically, whenever resume, whenever this depth goes, further depth goes, further depth goes, whenever resume, it will automatically go and this. So somewhere I have to definitely say that I have to go towards the next temp. So temp equal to temp arrow next. You can easily think that it's a kind of a traversal. So this will be needed and I'll go. Now, visited is every time being corrected, printing is happening, and accordingly traversal is happening. Till now, I have not used parent. Parent array nowhere updated. How to update? Updation will mean I have to update it correspondingly at some place. And where the parent is known, not in the previous module. Here, no idea who is the parent because no recursion started, no adjacent started, no area who is the parent. So I can't do the parent change in this module. I will say the parent change is possible here. So probably this is the place where I know that a parent of this adjacent vertex is nothing but I. So this is the time I will change my parent. But that also means for those which were uncovered, parent should remain -1, or those who remain having no parent, parent should remain -1. And I have not still initialized my visited and parent. So initialization of parent as well as visited array also needs to be handled. That we have not yet handled. Where to do this? So these two arrays also need to be initialized somewhere. And of course, they cannot be into this DFS. So they have to be where? I will say, before I start my DFS traversal, I must have here initialization. So that anytime DFS is started, my initialization of the visited array and of parent array. This I'll put intentionally brackets so that you remember that this is a kind of array. So I have this. So I will say this initialization and parent. So this you have to do here. Initialization will definitely mean a loop to be taken, and for I is equal to 1 to n, visited I equal to 0, and parent I to be -1, something like that. So this is what is going to be the overall algorithm. So by saying this, effectively my logic is over. Code is more or less ready, and you have to implement this. More or less it is ready. Rest fine tune you have to do. I'm not going to show the full code. Try to complete and run it and check, complete, run and check for all possibilities, and then maybe you will find it good. Then also must to read from the book also something. Must to read from the book this part. But when you read from the book, there will be certain changes visible and you might get confused. Because other algos will use that, the book's logic. I am also going to resume from the book's logic. So must read from the book. Certain changes or in the book compared to our discussion. So you should know so that you don't get confused. Compared to our discussion, compared to how I taught today's discussion, there are 3 changes which I should tell you. Then you should remember while reading the book. So once you have implemented, you should first implement this, then do reading from the book. First change, in the book, instead of visited or traversed, that they are using the word color. Instead of saying a visited word, the book is using a color where they say 0 means white color, and white means effectively untraversed or unvisited. They use color coding as 1, which they say is a gray color, and gray means with a traversal started, or it is started the traversal. It is not untraversed, but it has been started. And 2 means it is completed, and that will be called as a black color, completed. But for us, at most of the time, we are not bothered. We are treating this as equivalent, or for us same, no difference. So I say once it has become 1, it is as good as traversed or completed. It doesn't matter, but in the book they will use it, saying that all vertices are initially white, As soon as I start with that DFS visit, they will be called, start of that visit will be becoming a gray, vertex becomes a gray, and once it is completed, it's all vertices get, or it's all adjacents covered, then all adjacents covered, all outgoing edges checked, all outgoing edges completed, or checked or done, completed, then vertex becomes black. So that is first change, which we have not used, but it doesn't matter for us. Black and gray doesn't matter, but the only word matters. They are using color. I said visited or traversal status. Second change. In the book, they are also using for each vertex the starting time and some time related issues. Time or counter. 2 times the time of finish, time of start. Not needed for the time being, so ignore. Not needed now, so just ignore for the time. Nothing to bother. Forget that this is being considered. Third change. We have taken 3 different arrays, namely graph, namely visited, and namely parent. In the book, they have single node structure having all these. For each vertex, storing its color, its parent, and the next pointer. Or next pointer means adjacency list pointer. So in the book, they are all considered the same. What does that mean? They say that I have, let's say, main graph or main graph structure, where in each structure I store color, I store parent, and a pointer. For each vertex, this is the structure. So if you see carefully, it is nothing but equivalently for us, this whole data is nothing but for us, it is visited and we have taken at a global one. For us, equivalently, this is nothing but a parent. And for us, this all was the graph. So in the book, our 3 structures are separate. In the book, they are single. We have taken one separate structure for visited, another separate structure for parent, and another separate structure for the pointers, graph. And book has effectively one structure combined. So one structure will mean no global array needed and everything to be accessed from this index on. So your choice, the way you want to implement, but mine one is easy and you will find it more comfortable to start with. Once you are good, later you can try this. So here you have to declare a new structure or a new kind of a main node. As you have another new structure which you need to declare as a main node. And within this main node, like in the book, it will become another structure, another overall structure to be declared, where you will declare this new structure having this field, this field. From this onwards, things are the old one itself. Like for node 1, I said I have node 3, then I have node 5, node 2. So this node is old node itself, but this is a new node, new main node, and you have to do some additional programming to do this. So later you can try this, but initially for today's discussion, you later use this. For today's discussions, use separate visited global visited array and parent as a global array, and graph you have already declared. This you can use as a node star graph, this, as we have done for reading, or we have done for outgoing vertex edges, outgoing edge count, etc. So whatever we discussed in the previous lecture, we have used this. So today's discussion, just add these things and then you will be comfortable to use this. So this you have already practiced, hence it becomes easy, and then taking two extra arrays will become easy. Having said that, let me wind up there and stop discussions. Let me stop sharing and then stop recording also, so that now I'll end up this. Stop.